Okay, so we'll go back to another video. So here we have two little nice identities we like to verify dealing with binomial coefficients, and we have that n choose 0 subtract n choose 2 plus n choose 4 minus n choose 6, so on and so forth. It's an alternating series, is equal to the square root of 2 to the power n times cosine of n times pi divided by 4. And so we have, what's nice is that we have the n choose k for k are even indexes, verifies that this is the following, and then the same thing over here, but except we're dealing with odd indices, and that we have sine of n times pi divided by 4. So it's actually a little nice relationship that we like to verify in terms with binomial coefficients and something with trigonometric functions. It's nice that we can actually start off that, as you can see, and you can guess with binomial coefficients, we could start off that for one, everything's in terms of a partial sum, or rather infinite, as it goes on forever, that we can use the binomial theorem as a good starting point and start with the verification from the left to the right hand side. Not so much going on that needs to be taken heavily and thought of, because it's actually, the workload is pretty simple from here. But in between that entire process is actually, you get to see some nice complex numbers involved. So that's another thing to give away from here. But how would we approach that? We'll get to that in just a sec. And it's also nice that we don't actually have to do two separate proofs, that we can actually just do one at a time, but then it actually follows from the same procedure with the second proof as well, that altogether two results in one. So with that, let's actually just jump right in. The binomial theorem, we have that for some x plus y, and then to the power n is equal to our partial sum. So k is equal to 0 to n of n choose k of x to the power n minus k times y to the k, or the same thing for x to the power k times y to the power n minus k. Okay, so with this, that's a good starting point. So let's say if I chose something for the following inputs for x is equal to 1 and for y is x. So I have 1 plus x for that binomial. 1 plus x to the power n. And so that's equal to the expansion over here, n k is equals 0 of n choose k. So if I plug in for x is equal to 1 over here, so it's 1, so it's always just going to be 1, so that actually just vanishes, quote unquote. Then continuing forward, we put the x, so that means I have x to the power k right here. Okay, so let's actually expand this out. So I have the expansion is written as follows. So we have n choose 0, then with x to the power 0, which is just 1. Then I add this with n choose 1, then x to the power 1, then plus n choose 2, then x squared. Keep going on, so forth, and so we end off with n choose n, then multiply with x to the power n. That's the expansion we have so far, so let's actually substitute something for x over here. Why don't we actually substitute x equals I, lowercase I. Let's put this over here, sub x equals I, and so then we'll have this following expansion over here, so we have 1 plus I to the power n is equal to just n choose 0, then plus n choose 1, then times I, plus n choose 2, then I square. Keep going on, so forth. So endings off with n choose n, and then I to the power n. And so everything is with the imaginary unit I, so that means we'll have to separate everything from the reals and the imaginary part. So let's actually do that. So interestingly, this is not that difficult to see that anything with I square, I to the fourth, or even n to the 0 is just on its own. Those are the real parts. I square is always going to be equal to -1, then I to the fourth. So every with the even indexes is going to alternate between -1 or +1, but that's still considered part of the reals. So that means right here we have n choose 0, then add this with, well, rather subtract, because I have a I square. So that means subtract n choose 2, then plus n choose 4, then subtract n choose 6, then plus n choose 8 minus, it alternates for the even indices. Okay, so we can just cut that point off here. Well, let me at least add the ellipsis, so it actually continues on infinitely for the evens. And we do the same thing, but now this is associated with the imaginary unit I, and you can see that it's going to everything in terms of the odd indexes. So n choose 1, then subtract n choose 3, add this with n choose 5, subtract n choose 7, then follow the ellipse again, keep going for infinitely. So okay, so let's verify that so far that the left hand side 1 plus I to the power n so far is equal to this following expansion over here. So what's nice is that let's actually expand the left-hand side in terms of polar form. So 1 plus I to the power n. So I guess it's worth noting that specifically x plus y to the power n is written as the polar form r times e to the power I theta, then to the power n. So let me actually take that part out and then put it for that side of the room over here. So that's supposed to mean that r is equal to our modulus, the radius, x squared plus y squared. And then our theta over here is of course going to equal to the inverse tangent of y divided by x, theta being our argument in terms of we're looking at this at the complex plane. So from here, now let's actually expand this out in polar form. So 1 plus I to the power n, then that means if I just plug this in, so I have the square root of 2, then times e to the power I, then if we look at this in terms of how this is graphically put in, so it goes to the left, or it goes to the right 1, and then 1 unit up for the imaginary. So you can see where that argument forms, that it actually forms a 45-degree angle, aka that's pi over 4, and then to the power n. Okay, and then keep going expansion further, just distribute the n over here, so I have that this is the square root of 2 to the power n, then multiply with e to the power I times pi times 4n divided by 4. Then if I expand this out, of course, with using Euler's formula, so that's another way of saying the square root of 2 to the power n, then multiply with cosine of n pi 4, and then plus I times sine of n pi 4. And so from here, we see that this left-hand side is equal to this expansion over here. So the last part really generally is just to now equate the real and the imaginary parts. So the real part being is that this associated with cosine is going to equal to this real part, and then the imaginary is going to equal to this part. And actually, as I said, that actually completes the proof because it takes it's again equating. We actually did everything in one go instead of having to do 2 separate proofs. And so therefore that concludes that the square root of 2 to the power n cosine of pi times n divided by 4 is indeed just equal to n choose 0 plus or minus n choose 2, add this with n choose 4, and then subtract n choose 6, so on and so forth. So that's actually one side done. And then the other is that the square root of 2 to the power n times sine of pi times n divided by 4 is equal to just everything in terms of the odd indexes. N choose 1 minus n choose 3 plus n choose 5 minus n choose 7, then so on and so forth. And so that actually completes our proof for verifying these two identities over here, just like that. And so there we have it, as simple as it is, with the nice, and even with the nice relationship between in terms of both the binomial coefficients with complex numbers and of course with trig functions associated with that together. So yeah, that's pretty cool if you ask me.